Ladies and gentlemen, good afternoon. We are busy with the textbook of Cengel and Ghajar. Just in terms of a broader overview, let's look at what we've done so far and what we're going to do today. So in terms of heat transfer, last year you did in MTV 310, you did the first 3 chapters in the textbook of Cengel and Ghajar. You did the introduction and the basic concepts. You did the heat conduction, steady heat conduction, and then at the beginning of this year, I took over with this course. We started with transient heat conduction, and then we didn't do chapter 5. In the place of chapter 5, we did some fluid mechanics. We looked at the derivation of the Navier-Stokes equations, and that course, in any case, a CFD course, you're doing in a separate course. Then we did fundamentals of convection, chapter 6, external flow, chapter 7, internal flow, chapter 8, and today we're going to continue with natural convection. After natural convection, there's still a chapter on boiling and condensation, which we're not going to do in this course. We'll do it in the course of next semester. Then there's a chapter on heat exchangers that I'm going to do with you. That's very important. Then there are 2 more chapters on radiation heat transfer. And then lastly, there's a chapter on mass transfer that we're not going to do in this course, but which we will do in the next course next semester. So let's continue with natural convection. And let's just link natural convection with chapters 7 and 8. Okay, in chapters 7 and 8, what I brought to your attention when we started with those chapters is that it is actually all about determining the Nusselt number. And the Nusselt number, in general, is a function of the Reynolds number, the Prandtl number, and then the Grashof number. Okay. But in those 2 chapters, this never featured. Okay, so it never featured. We only looked at the Nusselt number as a function of Reynolds number and Prandtl number. So this is the effect of buoyancy. And that is specifically what we're going to discuss today, because what is now happening in chapter 9, where previously that term was not taken into consideration, in chapter 9, what we're going to do is we are going to take it into consideration. But firstly, without the effect of the Reynolds number, so we're going to say the Reynolds number is 0, there's a Prandtl number and there is a Grashof number, okay, with some of the work. But then we're also going to see that there are actually problems where the Nusselt number is not only a function of now the Prandtl and the Grashof number, but also a function of the Reynolds number, the Prandtl number, and the Grashof number, all of them together. So this is about the combination of forced convection and natural convection. If we look at chapter 9, in terms of the content of chapter 9, you'll see that firstly, we're going to look at the mechanism of natural convection, paragraph 9.1. Then there's going to be the equation of motion and the Grashof number, what it is, what it stands for. Then we're going to look at the different surfaces, the effect of different surfaces, specifically flat surfaces, because we would like to start very simple. And then we're going to make the surfaces more complex in the sense that paragraph 9.4, we're going to look at fin surfaces, so a surface with fins on, and then paragraph 9.5, inside an enclosure, and then lastly paragraph 9.6, where we have problems with forced convection and natural convection altogether. If you look at the chapter in general, all the main points, you will see that all the possible geometries are not contained in the textbook. So the textbook is just some of the most simple ones. The more complicated ones that many of you are going to experience, maybe in your research project or later on in industry, you'll have to go and look at literature to get it. But the fundamentals are exactly the same. So let's start with paragraph 9.1, which is about the physical mechanism of natural convection. Physical mechanism. But before we look at the physical mechanism, let's think of possible examples where natural convection is important. Do any of you have any suggestions where you think natural convection is important and when you see it or where you experience it? Electronic industry. Okay, there are lots of applications there. In the electronics industry, power transistors, TVs, DVDs, etc. All of them gets warm, temperature increases. And not all of them have a fan, to get rid of the heat. The heat is being disposed of by natural convection. The other examples are in cold areas, in cold climates, where next to the walls you've got these radiators, and in many cases steam are being circulated through it, and then the rooms are being heated by that surface whose temperature is very high. Okay, so that's another application. There's no fan. Then power transmission lines. Power transmission lines, temperature increases, but the heat is just being disposed to the environment. Then, in nature, where do we see it in nature? All the currents that we see in the air and water, the weather patterns are all being caused by natural convection. Then, all of you sitting here, your body, most of you are, if you're quite healthy now, at a temperature of 37, the ambient temperature is not 37, you give off heat, okay? And something is happening with that heat, so all of the heat is being exposed in this room, it all counts together, and that increases the temperature very slowly in this room. So that is natural convection. Then, also very important in terms of what we eat and what we drink, and I'm going to have some discussions on that just now. So in terms of what we eat, let's suppose you've got an egg. Okay, my drawing is not so good, but there's the egg, and it has been heated. It's very hot. Okay, and you put it on a surface. So what happens next to it? What will happen next to it is that this surface is going to increase the temperature of the air by conduction. Okay, and now that air molecule or control volume, if its temperature increases, its density becomes less. Okay, if its density becomes less than that of the surrounding air particle, it will move up. So what we have is we generate a flow field that typically will do something like that. In most cases, it's very difficult to measure. You would need very, very good instrumentation to measure it, but you can actually go and measure the flow field around it, and you'll see that there's air movement around the egg. Even more important is a cold beer. Okay. If you've got a cold beer and it's barbecue time and now the cold beer is outside. Okay, so this is the cold beer and this is the hot air. In this case, again, the air molecules next to the beer can, its temperature will decrease because of conduction. If its temperature decreases, the density increases, and the result would be that it would flow downwards. So you generate a flow field that does something like that. Okay, and we can see that the heated flow field and the cooled flow fields are not the same. Okay? So in general, people say heat rises. Is that correct? That's right, it's not correct. Okay, so heat doesn't rise. What will rise is heated air. So heated air will rise, or heated water will rise, but heat doesn't rise. Okay. You all did buoyancy of, for example, a ship. Here's the ship, and here's the water. It's in the sea. And this is typically the water that is being replaced by it. And then you've said that the net force is equal to the weight of the ship, W, minus the buoyancy force. And the weight would be equal to rho of the ship, S for the ship, okay, G multiplied by the volume that is being displaced, minus rho of the fluid, the volume of the ship that is being replaced, multiplied by G. Maybe my derivation is not so correct, but you can go and check it. You've done that in the first and second year. So the result of it is equal to rho S minus rho F multiplied by the volume that is being replaced, multiplied by G. And that is Archimedes' principle. You all know that. Okay? That change in density. Now what's very interesting is that if you've got a spacecraft, let's suppose there's a spacecraft and it's full of air, okay, and it is outside in space, okay, where G is equal to 0, when G is equal to 0, then there can be no natural convection. Even although inside the spacecraft there might be air, there cannot be natural convection because G is equal to 0. Now, this density distribution can be written in terms of temperature differences. And you need to go and look at your thermodynamics to do it. I'm going to jump it a little bit to show you the result, but you can go and check it. And it is being written in terms of what is called the volume expansion coefficient. The volume expansion coefficient. And this volume expansion coefficient is equal to beta, and that is equal to 1 divided by, and take note, this V I'm putting in here is not the dynamic viscosity, it is specific volume, small v, for specific volume, multiplied by partial dV dt at a constant pressure, and that is equal to 1 divided by rho, partial d rho dt at a constant pressure, and the units is 1 divided by Kelvin. And if you do that, you can actually go and show that beta is approximately equal to minus 1 divided by the density multiplied by the change in pressure divided by the change in temperature. And that is equal to minus 1 divided by rho. Rho infinite, what is rho infinite? Rho infinite would be the density far away from the object where it is a constant value. Okay, so here the density is something different. Okay, but if you move it away, then that would be rho infinite. Okay, so rho infinite minus rho divided by T infinite minus T. So again, that would be T infinite there, far away from the beer can, where that temperature is not equal to the temperature on the wall of the beer can. Okay, so what this is all about is the fact that you can now go and write that the change in density is equal to rho multiplied by beta multiplied by t minus t infinite. And that is equation 9.5 in your textbook. And it is actually quite an important equation because it is going to be used somewhere else. But what this equation shows us is that this change in density is the driving force for natural convection. And the natural convection will increase if beta increases. Now, where do you get the values of beta? Beta values are given in the tables in your textbook, firstly. So if you go and look in your textbook, you might have seen them so far. You didn't know what to do with them. Now you know what to do with them. Okay. However, very important, do not confuse it with the fact that beta for an ideal gas is approximately 1 divided by the temperature. And this temperature, of course, must be in Kelvin. So, if you do a few calculations and you work with air, then you can make this approximation very quickly, 1 divided by the temperature. However, remember it's an approximation. There are more accurate values available, and rather use them. But in some cases, you can make this assumption. Okay, so if we now look at what happens with buoyancy in terms of next to a body, what determines this flow field? Right, now if you go and look at the fluid mechanics of it, what is important is that it is about the forces which are going to be in balance in terms of the friction forces and the buoyancy forces. Okay, so the friction forces and the body forces. How they, not the body forces, the buoyancy forces. Okay. The interaction of those two with each other is going to determine the flow field around the body. Now, these flow fields, there are instrumentation available that you can actually go and measure or determine the flow fields around bodies with natural convection. And that, the instrumentation is called an interferometer meter. And what it does, it gives you plots of isotherms. And these plots of isotherms are being determined by measuring the density around a body, and they make use of the index of refraction to do that. So it is all about light, and the result of that is, and I don't know if you've seen it, but in your textbook, for example, there are 2 examples of that. There's an example of a flat plate with laminar flow, and then you can see these lines like that. And it gives you an idea, a visual idea of what is happening around a body. Okay. And then there's another photo of also a flat plate. However, take note, they don't show the beginning of the flat plate. They just show a part of the flat plate, and they show it in turbulent flow. And in turbulent flow, you'll see almost things like that. They're totally different, the flow paths. So that instrument can be used for eggs, beer cans, etc., to get an indication of what happens with a flow field around a body. If the flow fields are very, very small, the velocities are very small, then they are very, very difficult to measure. But in some cases, the velocities can actually be quite significant, and I'll get to it just now. And then obviously it can be determined. So paragraph 9.2 is about the equation of motion and the Grashof number. The equation of motion and the Grashof number. So the equation of motion in terms of natural convection starts by deriving it for the flow around a flat plate. And the flat plate is in a vertical position. And that is, in that direction, the y-axis, and in that direction is the x-axis. And this plate is being heated to a temperature Ts. So that is the temperature on the right-hand side of the plate. While around it we've got a stationary fluid with a velocity u which is equal to 0, and we've got a temperature and a density around it. So that is what is happening around this plate. Okay, now what will be shown is that, firstly, the boundary layer is going to develop, because this flow field, as we can see here, and you've done external forced convection, there must be a boundary layer. Do you agree? Okay. Now the boundary layer in this case is going to look a little bit different. It's going to have something, a profile like that. Okay. So next to the wall, the velocity must be equal to 0, but we've got flow there, and as it goes further and further away, the velocity again somewhere must be equal to 0. So the velocity profile looks totally different than, for example, the velocity profile through a tube. So there is u as a function of x, velocity profile like that. The temperature profile, however, remember temperature is not a vector, so we're going to use the distance of a line to show the value of the temperature. Here the temperature is going to be very high if it's a heated plate. Okay, that is the temperature, and it is going to decrease in that direction. So there is the value of the temperature there, and we're going to have a temperature distribution something like that. Now this paragraph, yes, question?
So shouldn't that x be a function of y and not of?
Sorry, yes, thank you. Here's a function of y. You could just check in your textbook. I'm not sure if maybe they've used x in that direction and y in that direction. Did they do it like that or not? Okay, doesn't matter. Okay. Okay, so, and that is then the temperature distribution. So that is temperature then also as a function of y. If you just look at it, does it make sense to you? Is that what you would expect? I think so, yes. Right. Now, of course, as you know by now, if we want all the equations, we need to have a control volume somewhere. And let's do that. Let's suppose here's our control volume. And our control volume is now going to be dy in that direction and dx in that direction. Okay. And we have on it the two pressure forces. So this pressure, if that pressure is equal to P, then that pressure there must be equal to P plus partial dP dx multiplied by the distance dx. And if that is the shear force tau, okay, then that must be the shear force in the opposite direction of tau plus partial d tau dy multiplied by dy. Okay, and this paragraph is now about, firstly, the equations of mass, of course, momentum, and energy, as you all know. And that you've done in chapter 6. So in chapter 6, you have derived the equations of mass, momentum, and energy. Now in those equations, that one and that one is not going to change. The only thing that needs to be modified is the momentum equation, because previously in the momentum equation, buoyancy forces were not included in the derivation. Okay. So if you now go and specifically take this buoyancy force, okay, that you write like that, with this into consideration, and you're going to put it into the momentum equation. We don't have time to do it. It is very simple, and it is given in your textbook, so I'm skipping it a little bit. If you're going to do it, then you're going to have the x momentum equation. Let me write it like that. So the x momentum equation, you're going to get u multiplied by partial du dx plus v multiplied by partial du dy is equal to the kinematic viscosity multiplied by partial d2 u dy plus, and now this term g multiplied by beta multiplied by t minus t infinite, and that is equation 9.93 in your textbook. 9.93. So that is the momentum equation, exactly the same one that you had previously, but with the buoyancy force included in the momentum equation in the x direction. This needs to be solved. How do we solve it? Well, by looking at the boundary conditions. Okay, the boundary conditions would, for example, be with a velocity on the wall, u is equal to 0. Okay, and in this case now, at this point, the velocity will also be 0. So 2 points where it is equal to 0. And for the temperature there, it would be equal to Ts. Okay? And this temperature there would be equal to T infinite. So using those boundary conditions, you can then get and solve the momentum equation. But what is important in it is that the following, after jumping a few steps, so it is in your textbook, you can go and look at it. What now pops out here is the following non-dimensionalized group, which is equal to g multiplied by beta multiplied by Ts minus T infinite multiplied by Lc to the third divided by the kinematic viscosity squared. All right, what is Lc equal to? Lc is the length of this flat plate. Lc, the characteristic length. And this is called the Grashof number. So the Grashof number, a non-dimensionalized number, which gives us an indication of the buoyancy force divided by the viscous force. Two forces. The ratio of buoyancy forces to viscous forces. While with the Reynolds number, okay, which is equal to rho v characteristic length divided by the viscosity, or VL divided by the kinematic viscosity, is the ratio of inertial forces to viscous forces. Those two. Okay. So Grashof buoyancy to viscous, Reynolds inertial to viscous. Now what is important is that in forced convection, we've used the Reynolds number to tell us if the flow field is laminar or turbulent. You remember that? So for a flat plate, approximately the Reynolds number is about 1, 2, 3 multiplied by 10 to the 5. If it's smaller than that, the flow would be laminar. If it's larger than that, the flow would be turbulent. For a tube, circular tube, it is about 2,300. Now, if we've got natural convection, if you think of this beer can, there's no velocities that you can actually measure. So now we use the Grashof number, and the Grashof number is going to be the one that now tells us if the flow is laminar or turbulent. Okay, so it just replaces the Reynolds number. So, where previously we've got the Grashof number, for example, for a flat plate. Okay. So if we've got a flat plate situation, then for a flat plate, let's just use one value here. If the Reynolds number is smaller than 5 multiplied by 10 to the 5, the flow would be laminar. If it is larger than that, it would be turbulent. Okay. Now, for natural convection, when there's no pump, when there is no fan that drives the flow around the flat plate, then it would be 10 to the 9. Okay. So if the Grashof number is now smaller than 10 to the 9, the flow would be laminar. And if it's larger than 10 to the 9, then the flow would be turbulent. Take note, this is for flat plates only. If we change the geometry, it would be different values. You understand? Okay, now look at the following interesting case. Let's suppose we have a cylinder and it's very hot. Very hot cylinder, and we just leave it in the air. Okay. What is now going to happen is we're going to have the buoyancy forces that develops around it, and it is going to develop a flow field like that. The velocities would be very small in value, be very difficult to measure. Specifically, if the temperature difference between the hot and the ambient is not very large. Okay, so that is the one type of problem. Now, let's look at the opposite one. We take exactly the same sphere, which is hot, and we put a big fan here. Okay. What is going to happen now? Now we're going to have the flow around this sphere, the flow field, doing something like that. You agree? Okay. So this we call natural convection. Okay. This one is called forced convection. Okay. For obvious reasons. Do you agree? Now, let's look at the case where you start making this fan smaller and smaller. Well, not really the fan itself, but the flow field that it generates. You start making it smaller and smaller. What is now going to happen? We are going to get to a situation where this flow and that flow is going to combine. So, again, take note, there's my fan now. Take note, it's a small one. Small fan. So it can't produce a lot of air. And now, for exactly the same sphere. What is now going to develop is a flow field that's going to do something like that. Does that make sense to you? And this is called, if this is natural convection and this is forced convection, we call this mixed convection. So mixed convection. Right. Now, that is now great if I tell you this, but what you would like to know is, but when is which one when? When do I have forced convection? When do I have natural convection? And when do I have mixed convection? I think that one is easy. And I think that one is easy. But if I start making this smaller and smaller, then at a stage, you're going to wonder, but okay, now when can I say it is a mixed convection problem, isn't it? Okay. Now, we use for that the ratio of the Grashof number to the Reynolds number. Obviously, for both of them, we use the same characteristic length when we calculate the Reynolds number and the Grashof number. So if it is a sphere, then the characteristic length for both of these would be the diameter. Okay. If it is a long flat plate, it would be that length for the Grashof number and the Reynolds number that we will be using. So in general, what we can say is that if we've got the ratio of the Grashof number divided by the Reynolds number square, if it is larger than 1, much larger than 1, then we can say that the inertial forces are negligible and the natural convection dominates. Okay, so if you can't read it, the inertial forces are negligible and the natural convection dominates. So that is the first category of problem, and that would be the case for when the Grashof divided by Reynolds square is much larger than 1. If we have now the next case, this would be when the Grashof number divided by the Reynolds square, both based on the characteristic length, is much smaller than 1. Now, it's the opposite of that. Okay, so the inertial force dominates. Okay, and the buoyancy force is negligible. Okay, the inertial forces dominates and the buoyancy force or forces is negligible. Of course, there's not only one, because at every control volume there's more than one. Okay, and then the last category would then be when the Grashof number divided by the Reynolds number square is approximately in the order of 1. What we now have is that both the inertial forces and the buoyancy forces are equally present. Okay, now you can't read it. Both the inertial forces and the buoyancy forces are equally present. They're approximately of the same magnitude. Okay, this is the fundamentals of natural convection. So just to make sure that you understand it, remember, this flow field, what causes the flow field? The fact that at one control volume, if you compare that to another control volume, the density in a specific control volume is smaller than in another one. Therefore, if its density is smaller, it would go down because of Archimedes' principle. It will go down, okay, and this will cause the flow field to move down. In this case, it is being heated, so its density decreases and then it goes up. So the heated air, the heat do not go up, but the heated air, in this case, goes up. In this case, the cooled air goes down. Right, now this effect, this density difference, In terms of the thermodynamics, we can go and derive it as approximately something like that. So here it shows the temperature difference causes this change in density. That is what this is all about. However, to get the beta can be problematic. If you've got tables, it's not a problem, or if you've got the computer program ease, you can go and calculate it, or with other programs. You can also, if you make the assumption that the gas that you work with is an ideal gas, then you can say it is approximately 1 divided by the temperature in Kelvin. In many cases, it is quite an accurate calculation. And with that, you've got the change in density. If you now go and look at what happens on a flat plate, from a fundamental point of view, there will be a boundary layer that develops. However, this boundary layer is different than that previously, because previously the boundary layer would, in this case, increases something like that. If this fluid also goes in this direction, that velocity is equal to 0, and then it will increase, or it will look something like that. So in this case, we've got a boundary hydrodynamically, in which we've got a hydrodynamic boundary layer, and somewhere in it we've got a maximum for the velocity. Okay, so it increases to a maximum and then it goes to 0. Here is the temperature on the wall. The air, if it is air flowing around it, that temperature would be equal to Ts, that of the plate, and then it would decrease to that of the ambient temperature. Remember, this is not 0, except if it's 0 Kelvin. Okay. So this is typically how it looks like. Now, if we go and look at the control volume at all the forces, we can derive from first principles the mass equation of continuity, momentum, and energy. We've already done it in chapter 6. It's a lot of work to do it, so we're not going to go through it again. But in that is the momentum equation, and previously we did not take into consideration the buoyancy force. So if we go and do it now, then that term starts appearing, and if we get to the equation, we can actually non-dimensionalize the equation, and this term now appears, and this is the term that drives natural convection problems, because it is the ratio of the buoyancy force divided by the viscous force. So in natural convection problems, we are going to use this criteria to determine if the flow is laminar or turbulent, because usually we will not have a Reynolds number. So in most cases, they're not going to give you a velocity or a mass flow, because you don't have it. Okay. So therefore, we use this criteria to determine if the flow is laminar or turbulent, where in forced convection, we've used the Reynolds number. The Reynolds number, which is the ratio of the inertial forces to the viscous forces. So, for a flat plate, for example, if we've got flow over a flat plate and there's forced convection, there's a pump or a fan, then we can calculate the Reynolds number, and then if the Reynolds number is smaller than 5 multiplied by 10 to the 5, the flow would be laminar. If it is larger than that, it would be turbulent. However, if there's no forced flow over it, then we've got natural convection. And then we can go and calculate the Grashof number. If the Grashof number is smaller than 10 to the 9, the flow would be laminar. If it's larger, it would be turbulent. So this gives us the 3 possibilities for the flow field. Either totally natural convection, okay, nothing is forced around it, it is just a natural flow. Opposite to forced convection, where the flow is forced around it, and the effects of natural convection is negligible. In the third category, where both of them starts playing an influence now. And in this, of course, in some cases, this, if we start making this smaller and smaller, then this would influence the flow field. So if this becomes smaller and smaller, then the flow field will start moving up like that one again. So it would change. Now, when and how do we determine which flow field we have? Well, with this ratio of the Grashof number divided by Reynolds number square, if it's much larger than 1, we've got natural convection. If it is much smaller than 1, it's forced convection. If the order of magnitude is approximately equal to 1, we have mixed convection. Question?
So what would be considered approximately 1?
Well, it is like, what do you consider as a girl to be beautiful? It's one of those subjective things where there's not a good answer. Okay, so in many cases in engineering, there's not a good answer. Okay, it is something that is also being determined by the circumstances. It will depend on how important is your calculation. What will the effect be of it? In many cases, you just need to know an answer approximately. And remember, with many of the heat transfer coefficients, most of them are not even accurate to plus or minus 20%. So you must in many cases know this is approximately the answer. It's better than nothing. Okay. However, and that is the thing, if you are involved in where you develop a new product and you're competing against that of others, then that would start becoming very, very important. Okay, ladies and gentlemen, thank you very much.